Problem 23. Rodrigo has a very large piece of graph paper. First, she draws a line segment connecting 0, 4, and point 20, and colors the 4 cells whose interiors intersect with the segment as shown below. Next, Rodrigo draws a line segment connecting the point 2000 and 3000 to the point 5,000 and 8,000. Okay, again, he colors cells whose interiors intersect the segment. How many cells will he color this time? This is a very interesting problem. Now, let's first look at the example given, the simpler example, okay? So from 0, 4 to 20, okay, then basically what you're looking at is a rectangle which has length 2 and height 4, right? This dimension is 2, this dimension is 4. And 2 and 4, they have a greatest common divisor, which is 2, okay? Then you divide the region to 4 parts. And each one is a smaller rectangle, which has dimension 1 and 2, okay? And then when you connect 0, 4 and 20, the line segment is going to cross this point. Okay, then within the 2 gray rectangles, okay, then the line segment do not pass any lattice point. And then for this situation, he colored 4 boxes in total, right? 4 squares in total. Now, then consider the more complicated situation from 2,000 to 3,000 to the point 5,000 and 8,000. How many cells will he color this time? Then you see, okay, 2,000 to 5,000. The difference in X is 3,000. The difference in Y from 3,000 to 8,000. The difference in Y is 5,000, right? And these two numbers are pretty large, and they have the greatest common divisor to be 1,000. So when he starts coloring, then what he's going to do is he actually repeats many things, right? Let's say this is a grid 5 by 3. Okay, he starts from here, and then the segment is going to cross this vertex, right? So the segment, okay, the segment is like this. So basically, he's going to have 1,000 units that looks like this, right? 1,000 units that looks like this. Now, we only need to figure out how many squares he colors for each unit. Then we multiply by 1,000. That's going to be the total number of cells that he will color, right? Okay, then how many cells he will color for this unit? You know, so within this unit, the segment does not pass any vertex point, any lattice point within the domain, except the 2 endpoints. Okay, then how do you figure that out? So let's say this is 0, 1, 2, 3. We give the lattice points some index, okay, 0, 1, 2, 3, 4, 5. In order to start from this point and go towards this ending point, okay, what does the line segment have to do? The line segment needs to cross 2 vertical lines and 4 horizontal lines. Each time the line segment crosses a vertical line or a horizontal line, it will arrive at a new cell. It will move from one cell to another cell, okay? every time the segment crosses a vertical line or a horizontal line, it will move from one cell to another cell. So then how many cells does the line segment intersect with? Then you can think about it, okay? You start from this location, okay? Then encounter one line here, so move to another cell, another line, a new cell, another line, a new cell, another line, another line, another line. So basically, in order to go to the end point, so there are 2 plus 4 lines, which is 6 lines, right? And starting from one square, crossing 6 lines, so encounter 6 more cells. So this means a total 6 plus 1 equals 7 cells. Okay, so for each rectangular region like this, 3 by 5, so he needs to color 7 cells. Now this repeats 1,000 times. So how many cells he needs to color? 7 times 1,000, which is 7,000 cells. Okay, and the answer is C. Problem 24. Jean made a piece of stained glass art in the shape of 2 mountains, as shown in the figure below. One mountain peak is 8 feet high, the other is 12 feet high. Each peak forms a 90-degree angle, and the straight sides of the mountain form 45 angles with the ground. The artwork has an area of 183 square feet, the total area. The sides of the mountains meet at an intersection point near the center of the artwork, h feet above the ground. What is the value of h? Okay, so basically we have 2 isosceles triangles, and they intersect for a region which is also an isosceles triangle, right? Okay, so 183 square feet equals what? Equals the area of the isosceles triangle with height 8. So 16 times 8 divided by 2, which is 64, right? Plus the area of the triangle with height 12. So it's 24 times 12 divided by 2, which is 144. Then subtract the area of this triangle, which is h squared. Okay, so then what is h? H squared equals 64 plus 144 minus 183. You can calculate it. This is 25. So h equals 5 feet. The answer is B. Problem 25. A small airplane has 4 rows of seats with 3 seats in each row. 8 passengers have boarded and distributed randomly. A married couple is next to board. What's the probability that there will be 2 adjacent seats in the same row for the couple? So the probability equals the number of successful ways or the number of ways that we are looking for, okay, over the total number of ways, right? Okay, then how many ways in total do we have to seat these 8 people? So we first, what do we need to do? 12 seats, we choose 8 seats and ask them to sit over there, right? So this is 12 choose 4, same as 12 choose 4. 12 times 11 times 10 times 9 divided by 4, 3, 2, 1. Simplified. So 4 times 3 equals 12. 2 cancels with the factor 2 in 10. 45 times 11, 495. So this is the total number of ways. Now, how many ways will we have if we need two seeds in a row, two seeds next to each other in the same row? Okay, so let's see the numerator. Okay, there are different situations. First of all, maybe we have two seeds next to each other, and another two seeds, they are not next to any empty seeds. Okay, so there are two possibilities. We have two seeds in one row next to each other, and the other two seeds appears in two different rows. Or we have two seeds in a row next to each other, and the two disconnected seeds appear in the same row, but one is on the left, one is on the right, not in the middle. So they are not connected. They are not next to each other. So this is 1.1, 1.2, two subcases. Okay. Then second, maybe we have two seeds next to each other, and we in a different row, we also have two seeds next to each other. So we have two pairs of seeds. Okay, this is a second possibility, right? And a third possibility, maybe we have a whole row empty, and then there's another seed in the other three rows. So these are three different cases. Now, let's count how many ways for each situation. Let's first consider 1.1. So there are two seeds next to each other in one row, some row. So there are four ways to choose that row. Choose one. Four ways. Then once we fix that row, for example, it's the first row, okay? Then we either have this and this, or this and this. So there are two ways to have two adjacent seeds. Okay, so 4 times 2. Then we assign these empty seats to the other three rows. Because they do not exist in the same row, we need to choose two rows from the three rows. So there are three different possibilities to pick two rows out of three rows. Once we pick these, then each seat, so we just know the row number, right? And then there are three seats in each row, so there are three choices for each of these seats. So we have 4 times 2 times 3 cubed. So it's 8 times 3 cubed. This is case 1.1. Now let's look at case 1.2. It shares some similarities. First, we need to pick one row that contains these two empty seats, so 4 choices. Then in that row, in order to have two seats next to each other, there are two different ways, two different possibilities, times 2. Okay, then we have two seats in the same row but not next to each other. We just need to pick one row. So there are 3 ways to pick one row. Once we pick that row, these two seats not next to each other, so they have to be on the sides, two sides. So there's only one way, right? So this is 8 times 3, which is 24. Okay, now let's look at the second situation. So basically we have two pairs of seeds. Then, we pick two rows. There are two rows which have two empty seats. So 4 choose 2. Okay. And in each row with two empty seats, there are two different configurations. So multiply by 2, multiply by 2, right? And this is 4 times 3 divided by 2, multiply by 2, multiply by 2, which is 24. Okay. So this is case 2. Now how about case 3? The one row, there are 3 seats. So we just pick one row, which is 4 choose 1, which is 4. There are 4 ways to choose one row. And then, so all the seats are empty in that row, so we don't need to do anything. But then there are 9 other seats, and there's one seat which is empty. So there are 9 choices for that seat to be, right? So this is 36. Now we have gone through all different cases, then we just need to calculate the total number of possibilities. Okay, so this is 8 times 27. This is 8 times 3, 8 times 27. Together, it's going to be 8 times 30. So this is 240, right? 240 plus 24 plus 36. This is 60. So the total number is 300. Okay, so the number of possible ways to be able to accommodate this couple is 300. Remember, the total number of ways is 495. Okay, then we simplify this fraction, right? Numerator and denominator are both multiples of 3 and 5, basically 15. Okay, so this is 20. This brings it down to 20, and this is 33. Okay, so 20 over 33 is the final answer. C.